All right. I will minimize that for now. Okay, so we created this assignments directory. Remember we have some written assignments. These written assignments are starting off really small. The first assignment is section 1.2, and I just copied and pasted section 1.2 from the textbook into here. And this is to reinforce your understanding of overdetermined and underdetermined systems. Can you find a consistent underdetermined linear system? Can you find a consistent overdetermined linear system? In other words, give an example of a consistent linear system, overdetermined and underdetermined linear system. Use matrices. You don't have to use an augmented matrix. You can write it as A matrix X equal B.
Where is this?
This is at the end of chapter 1.
In the Blackboard.
In Blackboard, in the assignments content area, do a control F5.
Okay, there we go.
Okay, can you find an inconsistent underdetermined system and an inconsistent overdetermined system? Explain why you expect an overdetermined linear system to be inconsistent, even though it must not always be the case, and explain why you would expect an underdetermined system to have infinitely many solutions, although that is not always the case. Okay, so why would you expect an overdetermined system to be inconsistent? Yeah.
Because there are too many equations to all of them to be fulfilled.
Right. There's too many equations for a smaller number of unknowns to have to all satisfy. It's much easier for there not to be a solution. And by the way, that's 99% of the time as an engineer. After we leave college, we have thousands of data points, which each gives us another equation or another constraint for a small number of variables, right? And we're going to find ourselves wanting to find the least squares solution, which is what we're going to do later in a future chapter. Why would you expect an underdetermined system to have infinitely many solutions?
Because there's too few equations to firmly pinpoint a specific solution.
There you go. If you don't have enough equations, if there are more variables than there are equations, if you wrote it as a matrix, right, the maximum you could have is the number of equations, the number of unknowns as pivots, right? If you had more equations, that means you'd have more columns, which means you'd have, if you have too many variables, then you don't have enough rows for all your columns. Some of those columns are going to be free, right? You would expect infinitely many solutions or none. The thing about in both of these situations, you would expect an overdetermined system to be inconsistent. But what if your data points just randomly turned out to all sit on a straight line, and there are 12 of them, but they were all on a straight line? Okay, that's not going to happen in real life, but it could. I mean, it's theoretically possible. In an underdetermined system, it may turn out that if you had more rows, it'd all be zeros. Well, and then you have infinitely many solutions. It may turn out that, and we'll talk about this in 2 chapters from now, that you have the space, we're going to talk about the vector space of all possible solutions, and the right-hand side just isn't in there. Okay? Let's look at a picture of that. The only one we can draw easily, here, let's get up our new pen app here, is in 3-dimensional space, right? But I need my straight line draw. In 3-dimensional space, so I'm going to have to draw one of the axes in perspective. Then the space where solutions might exist might turn out to be a plane, for example. A plane passing through the origin. You know, I wanted to keep that. Okay, and yet our right-hand side turns out to be a vector out here, not on that plane at all. So there would be no solutions. This is the column picture that we're going to be striving for, an understanding of the space of all possible solutions, the column space, right? And the fact that there may be vectors that are not in the column space. They're either in the null space of A transpose, or they're in some linear combination of the two that's in between the two subspaces. Okay. And we need to understand this geometry pretty well because we're going to use it when we can't draw pictures and have to rely on our intuition. Okay. All right. Both people who connected remotely disconnected.
They might be having connection issues.
Yeah, but I might be having some connection issues too. But I'm still in the meeting. Usually if it's on my side, it just leaves the meeting. Okay. So all the assignments in Blackboard, unlike the assignments in WebAssign, are written. So you have to write them down on a piece of paper, take a picture of them, or digitize them somehow. And I'd appreciate it if you've had multiple pages that you zip them all up and then just submit one file. It's easier for you and me. Yeah.
When are these due, and how do I submit them?
It's in your grade book. I think this first one is due Thursday by the end of day, or Friday by the end of day.
Oh,
Thursday.
Thursday by the end of day. Because these are there are a total of 6 whole questions, right? And we've been discussing 2 of them, the ones that help you answer the other 4. And these written assignments are not meant to be hard. They're meant to give me an opportunity to look and see what you wrote. And I don't see any difference between an untimed online quiz and a written assignment. Right? The only difference is you write one on a piece of paper, and that's what I want you to do anyway. I want you to draw a picture, or write an explanation, or solve an equation so that I can see all the steps. What I don't see in WebAssign are all the steps. Although I do know that there's a problem I have to grade in WebAssign in one of the homeworks this week from last week, right?
no. I don't think so.
Oh, maybe that's in the calculus class. They actually asked a question where they asked them to give an explanation, and then, of course, the computer can't grade the explanation, so I have to go grade it. But it's only one problem. Okay. All right. Yeah. So where are we sitting now? In the wrong book? In the calculus book?
Yes.
Okay. So let's take a look at the real book, our book. There we go. And we're still catching up, so we're in 2.3, right?
Yes. Yeah.
All right. Now, I already hinted at how to solve some of the homework problems from section 2.2 by calculating the inverse. What the author expected you to do was write your unknown matrices A, B, C, D, and then create 4 equations and 4 unknowns, and then create a 5 by 4 augmented matrix and reduce it and figure your answer that way. And that's what most people did. Yeah.
Oh, I wasn't supposed to invert the matrix and solve it?
No. Technically, we were waiting for section 3 for that. So we can use those exact same steps, reducing a matrix using row operations, to calculate the inverse of an invertible matrix. Now, an invertible matrix has to be square, because it has to have the same number of rows and columns in order to be able to multiply it times another n by n matrix and get an n by n identity matrix, right? The inner and the outer dimensions have to match. But more than that, as you hopefully have seen by now in the YouTube video, in the 3 blue, 1 brown videos, some matrices squish in dimensional space, for example, 3-dimensional space down onto a plane or a line. And some 2 by 2 matrices squish 2-dimensional space down onto a line or a point. And these matrices may be square, but they're called singular matrices. So a matrix has to have, an n by n matrix has to have all of its columns or pivot columns, right? When all of its columns are pivot columns and it's square, it's invertible, and we refer to that as non-singular. If we have a nice non-singular matrix, we can actually determine the inverse okay? Pretty easily. Now, this is what inverses look like in college algebra or in high school, K through 12. And this is what inverses look like for a non-singular or invertible n by n matrix. It's important that you remember that singular and non-singular are adjectives that only apply to square matrices. If it's over underdetermined, we don't use the phrase singular or non-singular. Because matrix multiplication is function composition, A times B is the composition of linear transformation A and linear transformation B, as is B times A. And so we use the notation of putting the -1 up in where the exponent goes, just like we do for functions when we indicate the functions of the inverse of an invertible function. Yeah.
Is the identity matrix, is that the matrix that is n by n that has 1 on
Yes.
diagonal and 0s everywhere else?
That's right. And it represents the identity linear transformation, right? It maps every vector to itself. Because the first column of the product is the first element of the vector, and the second column of the product is the second element, right? Because of the ones. All right? And so we always write an inverse if we know that A is an invertible matrix with the -1. And in fact, invertible matrices have unique inverses. So you don't have to worry whether or not there are more than one, and that's because every column is a pivot column, right? So if you have a consistent system, and you will if it's invertible, right, then it's going to be unique because it's not over or underdetermined. Now, a lot of times what we'll do is we'll attempt to calculate the inverse of a matrix, and if we get that it's inconsistent, then we'll know that the matrix wasn't invertible in the first place. Does this make sense? We may look at a square matrix and decide, let me try to calculate the inverse. So I'll go through all the steps we're about to perform, and if we get no solution instead of a unique one, we'll know that it wasn't an invertible matrix in the first place.
What about the infinite case?
What?
What about the infinite case?
Well, remember, you only have it's square, so you're not going to have an infinite case. If it's not invertible, you're going to get no solution. If it's invertible, you're going to get a unique solution. Right? It's not underdetermined. It's square. All right. Now, there are other, better ways to determine whether a matrix is singular or non-singular. If you start trying to calculate the inverse or reduce the matrix into upper triangular form and you realize it has a free column, you're done. As soon as you know that a square matrix has a free column, it's not invertible, right? It's squishing space into a smaller number of dimensions, which is where the word singular comes from. It comes from linear differential equations, where if the possible number of solutions gets switched down to a smaller number at some point, they call that a singular point, which you probably, if you've had linear algebra or differential equations, you saw in chapter 5. There were regular points and regular singular points, right? And irregular singular points. Okay. So how do we invert a matrix like this? Now, with a small matrix, meaning 2 by 2 or 3 by 3, we can use chapters 3 and calculate the determinant of the matrix. And if the determinant is not 0, we know it's invertible. And if the determinant is equal to 0, we'll know not to bother calculating the inverse because it's a singular matrix. Okay? But how do we go about calculating the inverse of this matrix? It has columns -1, -1, and 2, 1. So let's scroll down a little bit. There you are. That's why I can't find it. So -1, -1, and oh, we still have that guy. So 2, 1. Now we want to. Wow, it's really hard for me to see the little dot. Can I get a bigger dot? No, I'm using the darkest color for drawing.
You can change the thickness of the writing just to the left of it.
Oh, right. Yeah, I can change the thickness of the writing. I'm worried about doing that. There should be a way to get a bigger cursor without changing the thickness of the writing. And I don't think changing the thickness is necessarily going to change the cursor much. Okay, So what are we going to do here? We're going to do row, oh, you have, you're back on. So we're going to take a copy of this. And we're going to create a partitioned matrix.
Partition.
Yes, a partition matrix. We talked about that. A partition matrix has sub-matrices. Remember your exercise where you were dividing a matrix into basically a diagonal matrix of smaller matrices along the diagonal, and it was easier to multiply them together?
The block matrix?
Yeah, the block matrix. Oh, I was using green, wasn't
Yeah, I was saying we were using green.
I? Okay. 1, 0, and we're going to partition it with the identity like this. Now, before I go through the steps, which should be very familiar, I want to write down the algebra of what we're doing. If we have matrix A and the identity as a partition, and we multiply it by A inverse, like so, then remember, in block matrix terms, we're going to take the first column of the matrix on the right, which only has one element in it, and multiply it by the first row of the matrix on the left, which only has one element in it, A inverse. So we'll get A inverse times A. And in the second part, we'll have the second column of the matrix on the right multiplied by the first row of the matrix and only row of the matrix on the left. Now, assuming that A is an invertible matrix, A inverse times A is the identity, and A inverse times the identity, anything times the identity matrix is itself. So, this looks very familiar. If we perform row operations on this 2x4 partition matrix until we have the identity on the left-hand side of the partition, whatever's left on the right-hand side will be the inverse. So we're back to chapter 1, right? We're going to perform row operations. Okay, this is a familiar theme. All right, first we have to understand the linear algebra of what we're doing, okay, which will get harder every chapter. Then we're going to set up our system and then use row operations to solve it. Okay?
So it wasn't supposed to calculate the determinant and then use 1 over the determinant thing?
Oh, and you're going to find that the way that computers compute determinant and the way people do it are completely different. And the way people do it is row operations, not the Laplace expansion. Okay? In fact, there's a rubric I haven't had to use yet because we haven't gotten to chapter 3 that says never use the Laplace expansion. Okay? And if you do, I'm not going to grade it. Because what I'm going to do is I'm never going to put a 2x2 or a 3x3 on the test. I'm going to put a 6x6. And that means if you perform 6 5x5s and 34x4s and 122x2s, I'm not even going to bother grading it. I'm just going to give you a 0. Now I want you to use row operations. That's the whole point. This is the way humans solve these problems. And in fact, when it comes to problems like this is how computers do it. Computers do it using row operations. We're going to study the LU decomposition this week and the CR decomposition. And the computer performs the LU decomposition because we're going to find that the determinant of a composition, the product of two matrices, is the product of the determinants. And the determinant of L is always 1. So the determinant of A and the determinant of U are always the same number. And to compute the determinant of an upper triangular matrix, you just need the product of its diagonal elements, which is something we'll cover next week in chapter 3. Okay, so it's easy to do, right?
Oh, so I was not supposed to take my 3x3 and then break it down into 3 too?
No. What you're supposed to do is reduce it to upper triangular form and then compute the product of the diagonal elements, right? Row operations. Okay, so what do we need? We need a couple of row operations here. There we go. I'm going to subtract row 1 from row 2. And then after I'm done with that, I'm going to compute the negative of row 1. I have a tendency to like to try to do 2 things at once. And what do we get? Well, when we subtract row 1 from row 2, negative 1 minus the negative 1 is 0, and that was the whole point. And 1 minus 2 is a negative 1. And 0 minus 1 is a negative 1. And 1 minus 0 is 1. So we're halfway there.
Can we invert R1?
Well, yeah, but we're going to do that now. When we compute the multiplicative inverse of row 1, And all the negative numbers become positive, all the positive numbers become, become negative, and we're here. And it looks like we need to do the same thing here. We need row 1 minus 2 times row 2, and we need the negative of row 2. So we're going to get a new matrix. Oop. I don't need the arrow. And in this new matrix, first we'll subtract 2 times row 2 from row 1. But the thing about it is 2 times 0 is 0, and 1 minus 0 is 1. Okay, so 2 minus the negative 2 is 2 plus 2, which is 0, which was the whole point. And when I multiply negative 1 here by negative 2, I get 2. And 2 minus 1 is 1. And negative 2 times 1 is negative 2, plus 0 is negative 2. And we again wanted to find the multiplicative inverse of the elements of the second row, so all the negative ones become positive and all the positive ones become negative. And notice that now we have the identity in the left partition, which means that the right partition must be, from our algebra here, the right partition must be the matrix of columns 1, 1, and negative 2, negative 1. And what we're going to do now is check it by multiplying them together. And it doesn't matter what order we multiply them, in what order we multiply them. We'll take. I'm sorry? Yes, I know that. And so does the author. Okay, so it's certainly, I know that even when I was in an undergraduate, I kind of wondered if the author was just being sadistic. But the truth of the matter is, the author is trying to motivate you to want to learn this new material. I have gotten SPTs that said, I only needed to learn the first chapter. And I'm like, okay, then I'm sorry you passed. Because, yes, the technique we're going to use over and over again is the first chapter. But the linear algebra problem we're trying to solve is going to get more and more and more sophisticated as the chapters go along. Okay, so when we multiply these, I'm going to borrow the brackets from the last one. I'm still going to erase the entries. I just don't want to take time. Oops. Okay. So, if I multiply A times the first column of A inverse, this says the first column plus the second column. Does everyone see that? 1 times the first column plus 1 times the second column. So I'll just add the two columns together. Negative 1 plus 2 is a 1. And negative 1 plus 1 is a 0. The second column of our product, according to our matrix A inverse, says negative 2 times the first column minus the second column. Does everybody see that? Right? This is a definition of matrix vector multiplication. I'm going to multiply the first coordinate, negative 2, times the first column, plus negative 1 times the second column. Negative 2 times negative 1 is 2. 2 minus 2 is 0. And negative 2 times negative 1 is 2, and 2 minus 1 is 1. And since their product is the identity, we now know that this is the unique A inverse. Okay? And the beauty of this method is that it could be a 12 by 12 or 108 by 108, and the method would still be exactly the same. This is why we prefer this method. We don't need 15 different methods, basically. We need one method, and we're definitely going to do it that way. We're also going to find in Chapter 3 an exception, because we're going to find that column operations work just as well as row operations. And so in Chapter 3, when we're calculating determinants, it's okay to use column operations. Computing a determinant when a human computes a determinant, it's kind of like solving a Sudoku puzzle. how do I get ones in the diagonal, right? Or how do I get zeros everywhere else and just non-zero numbers along the diagonal? And you can use row operations or column operations. You just have to understand what the effect of those column or row operations is on the determinant.
Wait, there are column operations?
Sure. Can I add, aren't I performing column operations on the matrix on the left? I add one column to the next column. When I multiply on the left, I'm performing a row operation. This is what we're going to talk about this week. Okay. Oh, that would explain it. I'm going to put it closer so that no one confuses it with French. Okay, because it had k, and it was like, okay, we don't want that. All right. So, sometimes the way to find the inverse is to look at it and realize there was a homework problem like that and it confused everybody. It said, write B as a linear combination of the columns of A. And everybody wanted to reduce the matrix and then find the magic T from the infinite number of solutions that would give you an integer combination of columns. What the author intended for you to do was look at the columns and look at it and say, oh wow, B is 2 times the first column minus the third column, and just write 2 times A1 minus A2, 3 minus A3.
Oh, I wasn't supposed to go solve for B.
No, you're supposed to do it by, it's called solving by inspection. On a test, I will be really clear if I want you to solve something by just looking at it. But there are times when you can calculate a determinant, even of a really big matrix, just by looking at it. You look at it and you realize, oh, it's 0. Okay? And that's perfectly legitimate. On a test, if you weren't told to solve it by inspection, and you can say this determinant is 0 because row 2 and row 7 are identical, for example. If 2 rows or 2 columns of a matrix are identical, its determinant is 0 because when you subtract that row from the other row, you're going to row zeros, which means you have a singular matrix. Okay, you don't have enough pivot columns. You have a free column there. Okay. So this is the way the author calculates the inverse the first time. The author did it in her head and wrote down A times B and B times A and got the identity and said, oh, it's the inverse. And sometimes that is the best way to find an inverse. I call it coughing it up. You just say, it's the inverse. Multiply them together and get the identity. It must be the right answer because there can only be one inverse, right? What if we have to calculate it, though? By the way, that's why I calculated the inverse on the first one, since the author didn't. This is the way we learned to use it in the last section. Do it in the last section. And, we all decided we did not necessarily appreciate this method. Okay? But it does show why you can't invert a matrix that's not square. Because you'll get a system of equations that's not square. So you'll either get infinitely many solutions or none. So, how do we find the inverse using Gauss-Jordan elimination? Let's try a bigger matrix. So 1, 1, negative 6. Let's go to a new page. 1, 1, negative 6, negative 1, 0, 2, and 0, negative 1, 3. And the way that we'll invert this matrix is we will partition it with the 3 by 3 identity matrix and then use row operations.
Would it be a good idea to switch R2 and R3?
Nah. In fact, you don't want to, yeah, I stay away from switching rows when I'm doing things like this. Okay, 1, 0, 0. You could. 0, 1, 0. But both of them have a 1, a 0, and a negative 1 in it. I don't see any particular advantage of one over the other. So let's see. We're going to subtract row 1 from row 2. And we're going to add 6 times row 1 to row 3. And as we get into more and more abstract and more complex applications of matrices, it's going to be important for you not to confuse.
Where
It's,
is
I was thinking about this thing I was about to say here. Sorry. Not confuse what row you replace. You do not replace row 3 plus 6 row 1. You do not replace row 1 with it because you're multiplying by 6. And you don't want to completely stay away from 2 times row 3 minus 5 times row 2. You don't want to multiply both rows by something. You want to, the row you're replacing should be 1 times itself plus or minus a multiple of the other row. Or you're going to get the wrong answer. You get the right answer in this particular situation, and you'll get the right answer in almost all the problems you were given in Chapter 1, but in Chapter 3, when we're computing determinants, it'll give you the wrong answer. So always stick to an actual row, simple type 3 row operation. Add a multiple of one row to another and add that, replace that other row with the sum. Okay.
So we would have to multiply both matrices by a number. We should do that previously as a separate row operation, right?
Yes, you should. If you use a type 2 row operations, you should do it by itself, because it'll have a definite effect on the result. Okay, so we're replacing row 2 and row 3, so I guess I'm going to erase row 2 and row 3 from my copy. You know, I should have realized I can also do this. Okay. Not allowed? Okay. So, let's see. 1 minus 1 is 0. Does everybody know where I got the 1 minus 1? There you are. I knew you had to be around there somewhere.
You're doing R2, R minus R1.
Yeah, row 2 minus row 1. And 0 minus a negative 1 is 1. That's why I didn't want to switch them. And minus 1 minus 0 is minus 1. And 0 minus 1 is minus 1. And 1 minus 0 is 1. And 0 minus 0 is 0. Now we have a harder problem. We have to add 6 times row 1 to row 3. 6 minus 6 is 0, which was the whole point of our row operation. And negative 6 plus 2 is a negative 4. And 0 plus 3 is 3. And 6 plus 0 is 6. And 0 plus 0 is 0. And 0 plus 1 is 1. So in our row operations, where are you? There you go. We identified our first pivot and made it a 1. We identified our second pivot and made it a 1. And remember, the identity matrix is reduced row echelon form. So in the end, we're going to have to do a few more row operations to get it in reduced row echelon form. And now we're going to have row 3 plus 4 times row 2.
We also do R1 plus R2.
What?
We also R1 plus R2. Wouldn't that be helpful?
Yeah, but I usually don't do it that way, but we are definitely in the realm of there are going to be 57 different ways to go about doing these row operations, and all of us are going to choose a different path, and that's just fine. If we follow the rules, we'll always get the right answer. Okay, I didn't erase the 0 on the left because 4 times 0 is 0 plus 0 is 0. And 4 times 1 is 4, minus 4 is 0, which was the purpose of this row operation. 4 times negative 1 is negative 4, plus 3 is negative 1. 4 times negative 1 is negative 4, plus 6 is 2. 4 times 1 is 4, plus 0 is 4, and 4 times 0 is 0, plus 1 is 1.
Should we multiply row 3 by negative 1?
Yes, now we've identified our third and last pivot. And I'm going to go ahead and subtract row 3 from row 2, and then compute the negative of row 3 in a separate row operation, like so. And get a new page. Which I didn't need quite yet. And what all are we changing? We're changing this guy and all of these guys, but these guys we're just multiplying by -1. Okay, in the row operation above, -1 minus a -1 is 0. Yeah.
So, on the right side, don't you have to make?
Oh, yeah, but I'm just not done yet.
Okay, sorry.
That's all right. Is 0. And -1 minus 2 is -3. And 1 minus 4 is a -3. And 0 minus 1 is a -1. And as you guys probably saw, because I left off and went back to the row operation, we have to multiply everything by a negative. And now it looks like we can get into reduced row echelon form with one more row operation, which is row 1 plus row 2.
So in this case, getting to upper triangular form was not enough.
That's right. You need on the left-hand side the identity matrix. The reduced row echelon form of any non-singular matrix, meaning square, right, and all the columns are pivot columns, is always the identity matrix. The reduced row echelon form of every non-singular matrix is the identity matrix. This probably changes too. Okay. So we're adding -1 plus 1 is 0, which is what we wanted. We wanted to use 0 above the pivot as well as below it. Okay, 0 plus 0 is 0. It did not change. 1 plus a -3 is -2. 0 plus a -3 is -3. And 0 plus a -1 is -1. Did I make any mistakes? You don't think so? Well, let's see. -2 plus 3 is 1. Yeah, that worked. I'm just multiplying in my head. Let's see here.
Well, you always multiply the matrices together.
Yeah. Okay, so let's multiply. Well, what's sheet? The missing bar in the middle. I think that's a typographical error, so it looks like we got the right answer.
You could verify it in MATLAB.
That's true. You could verify it in GeoGebra. You could verify it in Wolfram Alpha, right? There are lots of different apps out there. I have a tendency to use. I'll spin up MATLAB if I'm using it for something else too. But if I'm not going to be opening MATLAB anyway, then I'll probably just use GeoGebra because it's a web interface and I don't have to connect VPN into campus and then bring up MATLAB and wait 5 minutes for it to decide if I have a legal copy. And
have fun with Photoshop.
yeah. Okay. This notation is an example of Cengage's own app for finding the inverse of a matrix.
Yeah.
Now, what if the matrix is singular? What's going to happen? So, new matrix, 1, 3, -2. Well, let's go ahead. The bar is missing. And I always draw the bar, and you should too.
Okay.
So they're going to perform the first set of row operations where they subtract 3 times row 1 from row 2 and add 2 times row 1 to row 3.
Uh-oh, there's a thing.
And now you've got a problem. You're done here because have we figured out that the third column of A is a free column? So it's a singular matrix. There's no inverse. Yeah. And sometimes that's exactly what you're going to do. You're going to get that far, and then you're just going to write down on the paper or on the exam, it's a singular matrix. We're finished.
No inverse.
Yeah. Okay. Using Gauss-Jordan elimination on a matrix A, B, C, D means that we're going to find a formula for the inverse of this matrix. And it turns out to be this one. Does anybody recognize AD minus BC?
That's what the determinant of.
It's the determinant of the 2 by 2. So in chapter 3, after we figure out how to calculate determinants the way humans do, we're also going to find a way to very quickly compute the inverse of a 2 by 2 and the inverse of a 3 by 3 using the determinant. Because it's going to be 1 over the determinant times the adjugate. So we'll have to have a new vocabulary term and a new matrix, which is the adjugate of a matrix.
Which is actually transposed times.
It's the transpose of the cofactor matrix. More vocabulary. The cofactors are the things that you are using when you perform the Laplace expansion. They're the determinants of the minors times -1 to the I plus j.
Right.
So there's a lot to it. Inverses of 2 by 2s are not too bad. After all, you have a formula. Now, in chapter 3, we will realize that this formula is 1 over the determinant times the adjugate. And we'll understand why A and D are swapped, but although B and C are swapped, they also have a minus sign.
But I assume that in this case, if you have,
Yeah.
in this case, if you have, if it's a singular, I assume in this case, if it's a singular matrix,
Then the determinant will be 0, which means you can't carry out this arithmetic because then you have 0 in the denominator. Yep.
Which is a problem.
That's why it boils down to, and the author is, this is like foreshadowing in a movie, right? The author is not saying this is the determinant, but hoping that we all recognize it as the determinant of a 2 by 2, right? And noticing that it's the determinant that can't be 0. If the determinant is equal to 0, then 1 over the determinant times the adjugate won't work because you put 0 in the denominator. We know that it's not invertible. If the determinant is non-zero, then we can perform this arithmetic. We can divide the adjugate matrix by the determinant and come up with the inverse, even if it's a 12 by 12. If it's a 12 by 12, none of us are going to want to do that. Computers don't use adjugates, and humans rarely use adjugates. We only use adjugates in 2 situations. When we're calculating a cross product, and when we're calculating the inverse of a 2 by 2 or possibly a 3 by 3. Yeah?
Wouldn't it be possible to come up with a formula like this for 3 by 3 or 4 by 4 matrices?
Yes, but it's a really complicated
Long
formula.
enough?
Yeah. It's a really complicated formula.
It's not fun.
Wait till I show you the formula for the determinant of a 3 by 3, and you'll realize, okay, I don't want to do that. Okay.
Isn't it just the same way we calculate the cross product?
It is. The cross product is the Laplace expansion. Not the one where you add the first column and the second column again and go this minus this. Okay? That's a shortcut that only works for 3 by 3s. So we won't use it at all because we don't like methods that only work for one kind of matrix. Does that make sense?
Okay, so we're not going to do the basket weave?
No, we're not going to do that because it only applies, it doesn't even work for 2 by 2s. It only works for 3 by 3s, and since it does, it's not very useful to us. We're interested in methods that we can use for any matrix, no matter how big. Okay, so the inverse is this piece right here. And again, how did the author know where to put the 2s and 3s? It switched the ones along the main diagonal, and it switched and computed the anti-diagonal by -1.
So the opposing diagonal is called their anti-diagonal?
Yes. Okay. Now, is it clear that the inverse of the inverse must be the original matrix? Okay, that turns out to be really important because one of the things that you're going to be asked to show is that if A is non-singular, then A inverse is also non-singular. How do you show that A inverse is also non-singular? You multiply it by A and get the identity and say, oh, it's invertible, so it's non-singular, right? After all, what is the inverse of A inverse? A. Because it's the matrix you multiply by A inverse to get the identity.
So could I say that?
And everybody goes, they always want to know, how do I start this problem? It seems so hard. And then eventually I tell them, and they're like, that's it. Yes.
So we could just say that by definition, the inverse must also be non-singular.
No, it's not by definition. What do you multiply by A inverse to get the identity?
A.
So now you have not only showed that A inverse is invertible, you found its inverse.
assuming that.
And that's an important piece of logic because there are other situations where we're going to produce the inverse by saying, well, wait a minute, isn't this the inverse of this other thing in the first place? Yeah.
There's a like a good way to write that. Assuming let A inverse equal matrix B, then B inverse must
Right. That's what I'm saying. So, how do inverses work algebraically? The first property is the inverse of the inverse is the original matrix. The inverse of a product is the product of the inverses. This is just like we learned, right, for algebra of real numbers. The inverse of a scalar multiple of a matrix is the multiplicative inverse of the scalar multiple times A inverse, which means that if C is 0, well, but that makes sense because 0 times a matrix, doesn't that multiply every element of the matrix by 0 and you end up with the 0 matrix? Okay. But what about the inverse of A transpose? How do we show that the inverse of A transpose is also A inverse transpose? And we're going to do a little linear algebra. The way that we show that's true is we multiply them together. We multiply what is the inverse of A transpose. So what we'll do is we will multiply A transpose by A inverse transpose. If I get the identity, not only have I found the inverse, right? So when you multiply two matrices and you get this, how do I put them inside the parentheses? What do I have to do to the product?
You switch them.
You have to reverse them, right? Remember this from last week? So when I try to put A transpose and A inverse transpose inside the parentheses, I have to reverse them. But what is A inverse times A?
Identity.
And what is the transpose of the identity?
Also the identity.
Right. So I ran out of room, so I'm going to move this down to the next page.
Well, and since we found the identity at the end, are we done?
Yes, because we found the identity at the end, we can conclude that A transpose is non-singular because it's invertible, and the inverse of A transpose is the thing we multiplied by A transpose to get the identity, the transpose of A inverse, because it was the thing. See, this is a perfect example. How did I show that if A is non-singular, then A transpose is non-singular? I produced its inverse. If A is non-singular, we know A inverse exists. We just don't know whether or not yet that A transpose is invertible. And we can transpose any matrix, right? That one's not restricted like inverse. And when we performed our linear algebra, we came up with the identity matrix, which means A transpose has an inverse, and it's the transpose of A inverse. So A transpose is invertible, and it equals this.
So if you're given like A transpose and A, and it tells you to find the inverse of both, you wouldn't have.
He would invert one of them and then transpose the other one.
Yeah.
That's right.
Instead of
And it's knowing this that you're supposed to learn from this class. Yeah.
If you ask, and A's not square in a question you ask,
Oh,
you say, well, we
if
can't
it's not
do-
square, it's not invertible.
Yeah, so. we
So
just
if I say
that.
if A is a non-singular matrix, you know it's square, right? To be non-singular, it has to be square. Its determinant is not equal to 0. It's invertible.
Okay.
So it was okay for me to write A inverse because we were given that A was a non-singular matrix. We were just asking if A is a non-singular matrix, is A transpose invertible? What's its inverse? It's the transpose of A inverse. That's why it's important to remember that singular and non-singular only apply to square matrices. If it's not square, you can't use those terms, those adjectives. Okay? Okay. Now it goes about proving it, which we already discovered. And because of what we discovered before, does it make sense that the inverse of a product reverses the inverses? And how would we prove that? Okay, so let's be more formal this time. Let's use the right part of the pen. If A and B are non-singular in by n. They both have to be the same size. So in this case, I'll have to say not just that they're non-singular, but they're the same size. N by n matrices. Then A times B is non-singular. Okay, and both of these are the kinds of questions you see on the exam as true, false, right? And we would say true to both of these, and then we would write down this little line of linear algebra that we wrote above, or the line of linear algebra we're going to write above. Okay, so what is the inverse of A times B? And I claim it's B inverse times A inverse. And why is that? What would be the next step? Multiplication by matrix isn't commutative, but is function composition associative? Yes, it is. So I can rewrite this A times B inverse times A inverse. And what is B times B inverse? The identity. And what is the A times the identity? A. And what is A times A inverse? I. So A times B is non-singular. Maybe we should pull this up a little bit because I don't want the recording to not see it. And the inverse of A times B is that matrix I used, B inverse A inverse. So you see that they get reversed just like they do with transposes, don't they? If I want to move the inverse inside the parentheses, I have to reverse them. What we have to be careful about is I can't go the other direction.
Divide B inverse.
If A times B is non-singular, must A and B be non-singular?
Not necessarily.
Yeah, the answer is not necessarily.
If I multiply a 3 by 3 and a 3 by 2, I get a singular matrix at the end.
That's right. Just because A times B is non-singular doesn't necessarily mean that both A and B are square. If A times B is non-singular and A and B are both square, that doesn't mean that they're non-singular. You can multiply two singular matrices together and get a non-singular one. I know, it's just crazy. If A times B and A are non-singular, B is non-singular, right? In other words, if the product of two square matrices is non-singular and one of them is also non-singular, you know the other one's non-singular too. And you do that using determinants. So we'll prove that in chapter 3. Okay. So basically, you get a unique solution when the matrix on the left is non-singular, which means it's square, it's not over or underdetermined, right? And it's not squishing space into a smaller number of directions. It's an invertible matrix. And the solution is going to be A inverse times B. Does this make sense? All the other times, we will either, if A is not square, we might get a solution, but it might not be unique. Or we might not get any solution at all. The system might be inconsistent. If A is square, if A is singular, then we get no solutions. And if it's non-singular, we get exactly one. And then, of course, you get to practice. It gives you a system of equations. You write it down as A times X equal B. You compute A inverse, and then you multiply A inverse times the B on the right-hand side to get the solution. Does this make sense? Okay.
Oh, that's one of the neighbors. We get the trivial solution.
Yeah. Now we have exercises. All right, and we're ready to start elementary matrices. Okay. The idea of an elementary matrix, it is a matrix you multiply on the left times A so that it performs a type 1, type 2, or type 3 row operation. For example, what is a type 1 row operation? That's where you
Interchange your,
exchange two rows. Okay. Look at D. Look at matrix D. If I multiply D times matrix A,
what is matrix A?
does it matter? It's just a 3 by 3 matrix.
No, it's not. It's one row operation from getting the identity.
Yes, it is very close to an identity matrix, but the ones aren't along the diagonal. In fact, what did we do to the identity matrix to get this one?
R2,
We switched row 2 and row 3.
R3.
Okay. In other words, we performed a type 1 row operation on the identity to get this matrix in the first place. Because we are exchanging a pair of rows, another verb for that in mathematics is we are permuting a pair of rows. In other words, this matrix is a permutation on the identity matrix, and that a permutation is that it reorders the rows. So that instead of going row 1, row 2, row 3, it goes row 1, row 3, row 2. And so we refer to type 1 elementary matrices as permutation matrices. Has been, yeah.
Okay, so do we always denote an identity matrix with I, or
Yeah.
would we want to denote an identity matrix with like I sub n, for example, for an n by n identity matrix?
Yes, you write I sub n when n is ambiguous, and you can write I if everybody understands from this problem that n is equal to a specific number.
Okay.
I almost always write I sub n, the 3, okay? But I'm the instructor, right? So sometimes I have to try to be very clear in the notes. Now, a permutation matrix is technically a matrix that performs a type 1 elementary row operations. The matrix I wrote below is a permutation matrix, but it is not elementary.
Doesn't that do two row operations at the same time?
That's right, it performs 2 row operations. Any permutation of the identity matrix will give you a permutation matrix. And when I multiply a matrix A on the left by that matrix, it will simply reorder the rows. But it's only an elementary permutation matrix if it exchanges exactly one pair of rows. Now, in a 2 by 2, there's only one pair of rows, so all permutation matrices are elementary because there's only one, the anti-diagonal. Okay, in the case of 3 by 3, it's very hard to come up with a non-elementary permutation matrix. But if we go to 4 and 5 and 112, it's easy to come up with permutation matrices that permute more than one pair of rows. And those are not elementary permutation matrices, so they're not elementary matrices.
So
They're just permutation matrices.
So we shouldn't use those.
I don't want to go that far. It's just I want you to understand when we perform the LU decomposition, we're only going to perform elementary operations. So we're only going to use elementary matrices. Okay? And in this case, yes, when we're performing the LU decomposition, we will on purpose restrict ourselves to elementary operations. Okay, so the first one is an elementary operation, but the second one is not. Both are permutation matrices, but not all permutation matrices are elementary. Okay? Because you have to exchange only one set of rows. Okay, so how do we do this? If we multiply this matrix here, by some matrix A. So you change the size of it, really? There we go. I'll just make it bigger. And I'm going to borrow this guy. And I'm going to make it a very simple elementary matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. The way that I calculate the product is I'm multiplying matrix on the right, usually A, by a very simple matrix on the left. And that simple matrix on the left says 1 times row 1 plus none times 0 times row 2 plus 0 times row 3. So I'll leave row 1 alone. The second row of our answer, of our product, is 0 times row 1 plus 0 times row 2 plus 1 times row 3. In other words, row 3. So, and the third row of our product is 0 times row 1 plus 1 times row 2 plus 0 times row 3. In other words, row 2. So it should be very simple to write down the row operation and then immediately write down the elementary matrix, because the elementary matrix is performing something very simple by multiplying a matrix on the left by that elementary matrix.
Then does it matter which order we multiply the elementary matrix? If we multiply the matrix by the elementary matrix, or?
Yes, because if I multiply a matrix on the right, I get an elementary column. I get an elementary column operation, not an elementary row operation. Yeah.
Is that supposed to be a 6 or a 9 in the final?
4, 5, 6. Yeah. Thank you. Thanks. I don't know why I did that. We'll save it. Okay. What's a type 2 elementary row operation?
When you multiply a matrix by?
Yeah, you multiply a single row by a constant, a non-zero constant. In other words, what if I wanted to multiply row 2 by a negative 2? Should be up there, right? There we go. And this is our familiar 1, 2, 3, 4, 5, 6, 7, 8, 9. So I didn't change the first row, and I didn't change the third row, but I'm multiplying the second row by a negative 2. So we take the identity and multiply one of the diagonal elements times a constant, and we get one that has 1s along the diagonal except for that one row where we want to multiply by a non-zero constant. And that product will turn out to be, all right, so now let's read the first row of our product. It says 1 times the first row plus none of the second or third row. The second row of our product says none of the first or third row, but minus 2 times the second row. And the third row of our product is none of the first or second row, but just the third row. Okay? So you see, when we came up with our row operations, now it's just as easy to write it as an elementary matrix. Okay, and what about a type 3 elementary matrix? So we have type 1 elementary matrices and type 2 elementary matrices. By the way, are type 1 elementary matrices invertible?
Yes, they should be.
In fact, what is the inverse of a permutation matrix?
Should be the element.
No? It's itself, right? If you apply the permutation again, won't it switch them back?
No.
Right? Permutation matrices are idempotent. If you multiply p times, or they're like -1. If you square it, you get you get 1, right?
So what's idempotent?
P squared equal p.
Oh, you're
In-
talking about type one.
Huh? Yeah, type 1 elementary matrices are always their own inverse. They're invertible, and the inverse is itself, right?
Okay.
Type 2 row operation. Is it non-singular?
So,
After all, what would be the inverse of multiplying the second row by the -2? What would undo it?
multiplying the second row by -1/2.
Yeah, multiplying the second row by -1/2. So it's easy to write the inverse, right? Wouldn't it be the matrix with columns 1, 0, 0, 0, minus 1/2, 0, and 0, 0, 1, and if you multiplied them together, you get the identity matrix. So they're easy to invert. Are type 3 elementary matrices invertible?
No.
Well, if I add 2 times row 1 to row 2, what would be the opposite of that? What would undo it?
Subtracting 2 times.
Row 1 from row 2. So, yes, it's invertible. Does this make sense? And it's easy to write down its inverse. Okay, so let's subtract 4 times row 1 from row 2. So, let's see here. This part's going to change. And that means this part's going to change. And now we want to subtract 4 times row 1 from row 2, right? Because we want to get 0 under the pivot. So we're not changing the first row. And we're not changing the third row. But we're adding -2 times row 1 to row 2.
Well, okay.
And isn't the inverse just changing the -2 to a +2? Adding 2 times row 2 to row 1? I mean 2 times row 1 to row 2. So I didn't change the first row in the product, and I didn't change the third row in the product. But, oh, -4, right? -4 times 1 is 4. -4 plus 4 is 0. -4. -8 plus 5 is -3. And -12 plus 6 is -6. Okay? So we're still going to perform elementary row operations just like in chapter 1, but we're going to perform them by multiplying on the left by an elementary matrix. Okay?
Okay, so you no longer want us to write R2 minus R1, you want us to write the elementary matrix.
Yes. I do. Let's save this so it doesn't go away. There we go. It hesitated, so I know it's saved. All right. Here's an example of multiplying a different matrix A times a type 1 row elementary matrix. So we are, well, this one's not elementary, is it? But it's still a permutation matrix. In the product, we want the second row, then we want the first row, and then we want, it's still exchanging row 1 and row 2, so it is elementary. Notice we use capital E for the matrix, capital E for elementary. When we have more than one, we'll use subscripts.
E1, E2, E3.
Huh?
E1, E2, E3.
Actually, no, we're going to use 2 subscripts. Because remember that the purpose of the elementary row operation is to get a 0 somewhere.
Right.
So we're going to use the 2 subscripts for the spot where we put the 0.
So EIJ.
So I would call this one E, since this one doesn't perform a useful elementary row operation, I would maybe call it E1, okay? But it gets a 0 right here, which is what we wanted. So we would probably call it E21, because it put a 0 in position 2-1. Does that make sense? That way we'll always know that we get unique subscripts. Okay, notice that this one multiplies the second row by 1/2, and that A is not square, but E is square, and so it has to have the same number of columns as that A has rows. Okay, and by multiplying by 1/2, it gets us a 1 in the second pivot.
So we would call that E22.
Well, no, this one doesn't follow that pattern much, but remember that when we perform the LU decomposition, we're going to go straight for upper triangular form. Okay. In this case, we're adding 2 times row 1 to row 2, but we're leaving row 1 and row 3 alone. So in the product, we leave row 1 of A alone, and we leave row 3 of A alone, but we would call this E sub 2,1 because we're putting a 0 in position 2,1 by adding 2 times row 1 to row 2. And we wouldn't carry out the multiplication, we would use the row operation. We say 2 times 1 is 2, minus 2 is 0, 2 times 0 is 0, minus 2 is negative 2, 2 times negative 1 is negative 2, plus 3 is 1. Right? We would still perform the row operation, even we know we have written it as matrix multiplication. Okay. So this is where we're going to start next time. And the author chose E1, E2, E3. But the author is now making the correlation between the row operation here, exchanging row 1 and row 2, and the elementary matrix that performs that row operation. The row operation, subtracting 2 times row 1 from row 3 and replacing row 3 with the elementary matrix that adds negative 2 times row 1 to row 3 in row 3. And 1/2 of row 3 here. Now notice the matrix is almost in reduced row echelon form. We would have to call this diagonal form. Okay. If we multiply A times E1, we got a new product. And this new matrix is here in the second spot. And then we multiplied it by E2 to get this one. And then we multiplied it by E3 to get the matrix in the end, which is in upper triangular form.
Okay.
Actually, it's in row echelon form.
So in order to do that, you write them in the reverse order you do them.
Right, because you're going to multiply from right to left. Right? Just like function composition. F circle G means X goes into G and then into F, and you go right to left. You would break all the rules. Algebraists in the 20th century tried to get everybody to do X of F instead of F of X, but nobody liked it. So we still, when we're doing matrix multiplication and composition, we go right to left. So this means perform E1, then E2, then E3, which gives us the same result as if we perform the row operations, which is our matrix in row echelon form. Okay? All right, so this is where we'll start on Thursday. You'll notice that the written homework's due during the week, but it also covers the stuff from, last week, not this week, not the new stuff we're learning. Okay. What we'll do next time is we'll perform the LU decomposition and the CR decomposition by using row operations, but we'll perform the row operations using elementary matrices, which will give us our L, our R, and our C, okay, and our U. Thanks. Thanks very much.